Welcome back. Let's get right into it. Yesterday we left off at an informal proof that if x is an even integer, then x squared is even. So today we're going to continue that. And basically the rest of this slide deck is just math examples. So some of them I'm going to have you do on your own, and then I'll show a solution afterwards, and others I'll go straight into the solution. For this one, I'll do it because it's, well, the first example in the entire class. But actually, I do have one or two announcements, mostly to do with questions that students have asked me and made me go like, I think everyone should know that. So two things are about the quizzes. The cutoff for each quiz's content will be the Wednesday before that quiz. So a student was asking about whether it would be the previous week or everything up to that, and yeah, it's until the class right before. Additionally, the wait list is very long, very horrible, and I'm aware that a lot of students are trying to get into the course. To that I say good luck. There is one quiz during the revision period. If you miss that quiz because you weren't attending classes or able to see any of the content because you were waitlisted, just talk to me about it, and the weight of that quiz will be shifted towards the final exam. And, oh yeah, I wanted to disclaim that since I'm technically a student. What do I mean technically? I'm just a student. I'm on the CSSA Discord server, but the policy there is that if a grad student is teaching a course, they're unable to see the Discord channel for that course. So if you want to interact with me on Discord, don't even try. I won't be able to see the channel. The discussion forums would be a lot better for that. Okay, let's get into it for real this time. I had to make a couple edits to the slides in order to fix an error found with some of the quiz details. It wasn't a very severe error, like the percentages of the final grade were off, but it made me lose my rough work for this proof. So I figure that's an opportunity to start by reviewing what we were doing last class. Let's recreate that rough proof. Okay, so we know that x is even, and we want to prove x squared is even, and x cubed is even. And because of the way and statements work, just math 1240 stuff, this is equivalent to showing two separate implications. So those two lines of math mean exactly the same thing. X being even leads to x squared and x cubed being even. That's the same as saying if x is even, then x squared is even, and that if x is even, then x cubed is even. So I'm just going to label these 1 and 2, and then we'll prove them both. So x equals 2a for some integer a, because that's the definition of an even number. Square both sides of the equation. And then manipulate it such that x squared is shown to be equal to 2 times some integer. And because multiplying integers together gives you another integer, if you want to be slightly cooler, you could say that the multiplication operation is closed under the integers. That's an even number. We're done. We start the other proof the same way, except we cube the number. And I guess, I'm not actually going to do it this way, but I guess you could show that x cubed equals x squared times x, and that those are both even, and the product of two even numbers is even. That's a totally valid proof method, but I'm going to stick closer to the definition for this example. And if you wanted to do that, you would also have to prove that the product of two even numbers is even, which is pretty simple. Cool. So, like I said at the end of last class, this proof has all of the necessary ideas for showing that the statement is true, but it's missing a lot of details. If you showed this to the marker, they'd probably get a little confused and then figure, they probably know what they're talking about, and then give you an okay mark. So now we're going to formalize this into something that a mathematician would be proud of. And this step's optional but highly recommended, and it's to stop using this stupid thing. Real mathematicians use a tool called LaTeX. That's LATE. And then what looks like an X but is apparently actually the Greek letter chi, I think. So it looks like the word latex. If you call it latex, I won't get mad at you, but you'll want to pronounce it LaTeX anyway in case you're dealing with a real snob. So I'll open up a code editor. Hopefully you all have something like Visual Studio Code installed. And I'm going to type out the full proof. If you've taken the course Comp 1002, Tools and Techniques 1, this will be pretty familiar for you. If you haven't, I actually recommend taking it even if you're in second or third year. It's a really useful course that shows a lot of, well, tools and techniques. The fact that I'm the TA for the course has nothing to do with my endorsement. So we're going to make a new file. And I'm just going to go text file for now. I'll throw it on my desktop and then delete it later. And then I'm not technically using LaTeX for this. Rather, I'm using a slightly different, or a completely different format, Markdown. Markdown is another really useful tool, and it happens to have support for all of LaTex's syntax. And I prefer using it especially for examples like this because it requires significantly less setup. So I'm just going to start typing, and the math stuff will become apparent later in the example. So we want to start or a good way to start proofs is by just restating what you've been told to assume. Oh, actually, here's already an example to show off LaTeX and Markdown syntax. Well, y'all probably can't even see that. That's a lot better. So we could say this, x is an even integer, but that'll look a bit unprofessional. You could probably type stuff like that already. So if we surround the math stuff with dollar signs, that gives us access to some amazing abilities, because sort of like how you compile your code into a program that can run, Markdown and LaTeX files are basically compiled into nicer looking documents. So now I've split the window. On the left is what I'm actually typing. You could think of it as my code. And then on the right is what that Markdown text translates to. You could think of it as your program. And see how x surrounded by dollar signs becomes a nice mathy x. Pretty cool. Not important, not super important right now, but later this proof even, we'll be typing stuff that would be really unwieldy to do in plain text. And then this will help us a lot. So, like the rough proof, we're going to show the two parts of the AND result separately. We want to type x squared, and we use a LaTeX syntax for exponents. So this thing, I think it's called a caret. It's what you get when you type Shift 6. X squared is even. From the previous step, this format with like numbering your steps isn't mandatory, but I highly recommend it because it makes it really easy to follow your proofs. Then I'm going to attempt a bit of syntax. I'm not sure about whether it will work. Okay, sweet. So if you surround bits of math with single dollar signs, it'll show up in line as part of the same line. But if you put $2 on separate lines, or 2 pairs of $signs on separate lines around your math, then it'll show up in the center, which is nice to be able to sort of emphasize important parts. Or if you're doing lots of algebra, you'll want to put it like this. So now this is the stuff I was just writing out earlier. Oh, and did you see that? It has compiler errors. Woo! So in this case, it's complaining that nothing is coming after the caret. And so far, this formalized proof hasn't really done anything differently from our informal proof, but now we're going to add an important bit of exposition. Just showing that x squared is 2 times something isn't really sufficient to show it's even. We're going to add an extra line that basically repeats what I was saying about how you can multiply integers to get integers. Because, of course, a proof doesn't come with a commentary or a lecture. It needs to include everything that the reader needs to understand the conclusion. And then this part's also really cool. I want to type A is a member of the integers. So I'm going to use certain keywords in LaTeX. A is in, now we want the fancy Z. That's going to be math BB. I think that stands for blackboard bold, because in the old days when people wrote stuff on chalkboards, this is how they would make letters look bold instead of like filling the whole thing in. And then these curly brackets sort of work like parameters to a function, Z, and then close the math section with another $sign, and boom, A is in the set of the integers. So it follows that the thing we got earlier, 2 times 2a squared, is in math BB Z. Notice how that got a different result when I typed the lowercase z. So, of course, this stuff's case sensitive. I do admit it's a bit annoying how the preview is shaking while I type. If you didn't notice that before, you're going to, sorry. I'm using Visual Studio Code because everyone knows and loves it, and I can easily put the source code, the markdown text, next to its preview. But if you're going to use Markdown or LaTeX in an assignment, and I strongly recommend you do, there are many other Markdown editors. I recommend Obsidian because it sort of merges these two windows into one. You write that second $sign, and then that stuff just becomes math. We call it an inline preview, I think. And then you can click on the math to edit that LaTeX syntax. And now we're just repeating that last step. So now's the time to type that second bit of justification. Like, since a is an integer, the result is an integer, but that's a lot of boring typing, and I want to point out, just in case you're not already sold on Markdown and LaTeX, that copy-paste is always a thing. It's easy. Now I'll just correct the stuff that needs to change. And that's looking good. Yeah, back in my second year, back when I was still writing proofs on paper and stuff, there's one time I had like don't remember how many pages, but it was a several page proof where I had a mistake near the beginning, and fixing it required multiple lines of text, and I had to rewrite the entire thing. I wish I had Markdown and LaTeX back then. So let's finish off the proof. It's always good to write this sort of conclusion statement so that the reader walks out of the proof remembering what you actually wanted to prove. It doesn't just cut off abruptly. Cool. We're done. This proof would get full marks, but also might want to include a square. Ta-da! In general, you don't need to worry too much about copying what I'm typing. Write down what I'm explaining along with the text by all means, but this proof I'm actually just copying off of a printout of the slides, so it's also right here. If you weren't able to type or write very fast and you missed some details, don't worry, you didn't miss a thing. Now we'll just quickly review the main takeaways from that example. So instead of writing the word "and," there's a symbol that looks like a little triangle that represents "and." I remember that as how it looks like kind of looks like an A. So P-A-Q means P and Q. So for any statements P and Q, if you prove them separately, you know that P and Q is true. Now we'll do an OR statement. So we know that x is a real number such that x squared equals 25. And we want to show that x is less than or equal to 5. So it's at most 5. So hopefully this seems a little too easy. If you think of numbers that you could square to get 25, probably only one number will come to mind, and that's 5. But there are always things that can trip you up, and most of them involve negative signs. So remember that negative 5 is also a square root of 25. So we have x is a real number. That's blackboard bold. And x squared equals 25. So this is kind of going to look like the reverse of that and example from just now. Instead of starting from one assumption and getting two conclusions, we kind of have two assumptions. X could be 5. It could also be -5. Who knows? Our assumption that x squared equals 25 means that either of those can be true, so we have to show that both of them lead to x being less than or equal to 5. In slightly more formal terms, we need to show that x being equal to 5 implies x is less than or equal to 5, and x being equal to -5 implies x being less than or equal to 5. We kind of just proved it, actually. Recall that our axioms consist of math works as you expect it to from grade school. And yeah, this all works. Obviously, 5 is less than or equal to itself, and -5 is less than or equal to 5. So we kind of did it, but we should formalize it too. So first part of the formal proof is that we recall that x less than or equal, you might be tempted to write it like this, but that's a comp sci way, and we're more immersed in the math way right now. In LaTeX, that's \lec, less than or equal to. So it means that x is less than 5. No special symbol for less than, because that's already on your keyboard. Or x equals 5. The slides spell out the word or, but that's obviously a lot of typing. Why type 2 characters if you could type 1? Or I guess this isn't going to be efficient at all in LaTeX. Why make the marker read 2 characters when you can make them read 1? The symbol for or, as you hopefully know from Math 1240 and or the readings, is a sort of V shape, an upside down and symbol. And how do we type that in LaTeX? backslash. That's the thing that comes before basically all of the keywords. Lore. Not for any amazing story or anything, but it stands for logical or. Yes. I was being a bit facetious. The marker does know the word or. You can use the English word in your proof if you want. It may just be seen as more elegant to use the symbol instead of spelling it out. So our first step, since x squared equals 25, by assumption, the only options are that x is equal to 5 or x is equal to -5. We proceed by cases. Another thing you hopefully know from past experience, proof by cases is essentially what this example is meant to show. We have two things that could be true. We don't know which one is true, but we know one of them is true. So we show that the thing we're trying to prove works regardless of which one is true. Oh yeah, like I'm adding some words, some stuff to the proof that's actually in the slides in ways that, in my opinion, makes it more clear. But the content, the actual ideas, should still be the same. They would both get full marks. In this specific case, I'm numbering the cases to make the proof by cases technique more obvious. So this part's suspiciously easy, but yeah, it follows directly from the axioms. We're good. So now, if x is equal to -5, then it's less than 5. So recall the thing that we recalled. X being less than or equal to 5 means that it's either less than or equal. In case 1, that the fact that x is equal to 5 directly implied that part of the or statement, so we were able to conclude that x is less than or equal to 5. In this second case, we had one extra step, just stating that it's strictly less than 5, which then implies what we want. I think that's a good example of how you should err towards showing details in proofs, and how the exact amount of detail is kind of a matter of taste, one that will come to you as you read and write many proofs. And we're done again. I have no idea why mathematicians do that square, but it's fun. It's like a little send-off for your proof. And this slide's the takeaway again. So if we know that, or if we have a statement we want to prove like P or Q implies R, then we proceed by cases. First, you suppose P and prove R, and then in a totally separate proof or bit of the proof, you suppose Q, not assuming anything about P, and prove R. And likewise, in the part with P, you don't assume anything about Q. Those are like totally separate things. You could think of them as like different functions in the same program that don't have access to each other's variables. Oh, this second point I think is useful too. I think it'll come up. Oh yeah, it did come up during our proof. So if we have proved Q, then for any statement, literally anything, we can conclude P or Q. So in this case, we had that x is less than 5, and we could conclude from that that x is less than 5 or x is equal to 5. Oh, question? Sorry, could you speak up, please? Oh, good question. I was referring to these bracketed steps. I'll make this a bit clearer. There. So, step 2 has... Oh, wait. Haha! I think this was the real thing you were asking about. Thanks for pointing that out. So yeah, step 2 has case 1 and step 3 has case 2. Now what was I talking about again? Yeah, we knew that x is less than 5, from which we could say x is less than 5 or x is equal to 5. Don't believe me? Make a truth table and then observe the true immutable truth of that technique. Now for another one. I don't know about you, but I'm getting tired of this. So we're going to let x and y be real numbers, assume that their sum is 10, and we'll prove that one of the following is true. Either x is less than or equal to 5, or y is less than or equal to 5. I promise I'll give y'all time to work on certain examples of your own on your own eventually, but all these exercises are introducing some new concepts, so I'm going to do this one myself too. So the big idea here is digging more into some things that follow from how the OR logical connective works. this little convention for showing the different things that can be implied from an assumption might be a little unclear, so I'm adding a little or right here. Previously, actually, no, it's meaning the same thing both times. In both cases, the thing we're assuming leads to at least one of those two possible implications being the case. So, how are we going to prove just this? We want to show that at least one of these is true, but the techniques we've been using won't quite work because from x plus y equals 10, we can't be absolutely certain that either one of these is true. We know that one of them is true, or both, but we don't know which. So we are in a bit of a rock here, but here's how we're going to solve this. We're going to assume that one of the possible implications is false, and then that will lead us to the other implication needing to be true. So we're going to assume that x is greater than 5 and show that that leads to x being less than or y being less than or equal to 5. I'll do that proof and then do a bit more explanation on what's going on here mathematically. So we're going to rewrite x plus y equals 10. Rewrite that as y equals 10 minus x. And because we assumed that x is greater than 5, then 10 minus x is less than. We flip the inequality because of the subtraction we're doing. And that 10 minus 5 is equal to 5. All this algebra shows us that y is, I'm going to draw an implication symbol to make it a bit clearer. It only has, this part of the proof only has to be as clear as it has to be to make sense to you, the writer. You're not going to hand this stuff in. And that, as we talked about previously, implies that y is less than or equal to 5. So we showed that if x plus y equals 10 and x is not less than or equal to 5, then y is less than or equal to 5. I'm going to check the next slide and see if it has a more generalized form of this sort of argument so I can explain it. Okay, yeah. So we have a statement like P or Q, and P is either true or false. Can't be neither, can't be both, can't be anything else. It's the rules we made up for math. So if P is true, then P or Q is trivially true, because we already know that at least one of P or Q is true. If P is false, then P or Q is only true if, and only if, Q. So we know that one of the statements is definitely false, so we need the other statement to be definitely true in order for at least one of those statements to be true, and thus for the or statement to hold. You'll never have to explain this if you invoke this technique in a proof. This is a standard argument. So if you're trying to prove an or statement, you could just go ahead and assume that one of them is not true and show that the other one must. That makes it so the other one must be true. In this case, we totally could have assumed that this one isn't true and then proved that x is less than or equal to 5. Would have been basically the same proof. But in more complicated cases, you'll have to put a lot of thought into which one you want to negate, and maybe accidentally negate the wrong one and realize that you've been proving nonsense. It's all part of the learning process. With 2 minutes left, probably less than 2 minutes if you account for seconds, I'm not going to bother formalizing this one. The proof's also right here. And I'll stop here for today. Tomorrow we'll do yet more examples. See you then.